Okay, so today, we'll be looking at the case study of combining analytical plus learn models. We'll spend some time on specific features, and then we'll look at learning models, but now in feature space. For example, with autoencoders, we'll look at contrastive learning, and very briefly look at GANs because these would be useful for some of the inverse reinforcement learning stuff that we left earlier. So, first let's look at the case study of combining analytical and learned models. So, let's take an example. So this example is this robot called as Hammer. So if you look at the system, it's a very small robot which has 4 legs. And just to give an idea of how big the system is, it's pretty small. Now, once you start going to these small robots, you end up using flexible material, which ends up being non-rigid. And when we are dealing with flexible, non-rigid material, that simulation becomes extremely slow, right? Because you need to do some kind of finite element analysis to do simulation, which ends up being slow. Turns out, for example, in this robot, simulation is almost 100 times slower than actually running the robot. So, one thing that we saw in the course was that, sometimes because reinforcement learning is so data inefficient, and then transfer policies to the real world. But in this scenario, this wouldn't really be possible because the simulation is so slow. So what can we do in such a scenario? So one possibility, seems like some of you have your audio on. So I would just request if you join the meeting, please mute your audio, and then if you ask a question, switch it on. So, we have the full model of the robot, which is very slow to simulate. But we could simplify the model. For example, all these things are connected with each other. We could have a simple model which is rigid, and maybe those couplings are no longer there. So it's a simplified model which I have. So now the simplified model is faster than real-time simulation, but it is not accurate enough that if I learn policies on the simple model and then I run them on the full model, it is not going to work, right? Because the policies will exploit some things about the simple model which will not work on the full model. And so this is something which we also encountered when we were doing domain randomization, that there's a mismatch between the simulation and how the real world is. So we are left with 2 options over here. One thing we can do is we can say, well, the simulator itself is slow, but what about we learn end to end and just have a neural network which can mimic the full model. And the neural network could be very fast to run. So that is one possibility. And that would fit in very nicely with some of the model-based work that we have seen. Right? For example, we saw like how if I have to manipulate a ball or a cube in my hand, we could learn models and then leverage those models to learn a policy. Right? So that is one possibility. Other possibility is that we could do domain randomization. Right? Maybe there is some parameter setting which would make this model be as close as possible to the full model. Right? So those are the 2 things that we looked at in the course earlier. But we also looked at is the fact that if we do a lot of randomization, for example, the red line over here is showing randomization with respect to body inertia. On the y-axis, the expected return. What you see is if you randomize too much, then yes, you are robust to a larger range of parameters, but the peak performance is also lower as compared to no randomization, or as opposed to having the right set of parameters. Right? This is something which probably you also saw in the last question of your last homework. It's domain randomization comes with a disadvantage. Now, if we just take this particular setup right? And if we take this and we train policies on hammer simple, which is a simple model, which is shown in the performance on the simple model is shown in gray, and the performance on the full model is shown in green, right, which is the post-transfer performance. What you see is the performance on the full model after training on hammer simple is pretty bad. So we can do, some kinds of domain randomization, input noise, but turns out in this scenario, it doesn't really help because it's just not some parameters which are different, right? I've completely changed, I've changed the physics substantially by removing the couplings and also changing the kind of material that I am using. So what can we do in such situations? Anyone wants to make a comment or take a guess or suggest a method to tackle this problem? No. Okay, so let's see one possible thing that we could do. So one idea one could exploit is to say, well, let's assume that I want to learn a model, and let's assume that we want to learn the full model, which is I start with X and A, and I want to predict my future states or go to my goal state. Now, if I try to learn this full model, I might require a lot of data because model learning will also consume some amount of data. So what do we do in that case? Or maybe the question is, can we reduce the amount of data that is used to learn this model? So now one thing to realize is that what will this forward model end up learning? The first thing it will learn is a nonlinear transmission, which is if I apply some torques to my motors, how are my legs going to move? If it is rigid system, then everything is rigid. But if you have some non-rigid materials, then that function from motors to how the legs move could be non-linear. Right? We can think of it in many scenarios, even beyond robotics. You can have non-linear dynamics. Right? That's the whole reason of using neural networks. The other thing you'll end up modeling are the contacts. Right? When my robot hits the ground, it applies a force and then it moves forward. Right? So I have to also model what are the next states of my leg after I end up making contact. But we can be a bit clever over here. For example, I can say the nonlinear transmission is actually some linear transmission plus residual. Right? And this residual models the difference between the linear and the nonlinear part. So if I have a linear transmission plus contacts, this is something I can do very easily with simulators, right? Because we have very good and fast rigid body simulators. And I can just learn the residual in my transmission dynamics. So I can use the simulator to simulate a bare minimum simplified model and just use learning where it is required. That is to compensate the model difference between what would have happened if I used a complex model versus what happened if I used a simple model. Right? So I don't need to relearn the simple model. And that can give us some data savings. So to make it more concrete, right, suppose I have my simple model given by this function f simple, where q and q dot is the state representation, which could be your position and the velocity, q dot double dot is the acceleration, and u are the actions. Right? So suppose f simple is a simple model, f full is a full model, but f simple is not equal to f full. So now what I can do is I can pose the learning as following, which says, I want to run the simple model. How about, I want to get the output which I would have got in. So suppose there was an action u full, which I put in the full model, I would have got some output, right? So can I take the U full, which is the action which goes in the full model, and learn a function which converts it into an action that I can feed into the simple model so that the output of the simple model and the full model can be similar to each other. So what I have done is I've transferred the nonlinearity now in the action space. Right? I'm saying, suppose if I put U full, I would have got a desired outcome. But if I put U full in the simple model, my prediction is going to be way off because my simple model is not the same as F full. So how about I modify U full through a neural network, which is this function k hat over here, so that I come up with U simple, which is something I can feed into the simple model so that the output of the simple model becomes same as the full model. And turns out in this problem and in many other problems, just modeling what is required is sufficient. So for example, over here, if I show you the position and the velocity evolution over time, and if you look at the true model, which is given in the black, the blue model is the dynamics predicted for the simple model, and the orange line is showing the predictions from this residual model. And because we're only learning limited amount of things, this can be very fast. For example, we only require 12 seconds of data. And running this residual model is 47 times faster than simulating the full model. And what this means is I can use this learned residual model as my simulator and then do learning in that. And then for example, we can get this agent and it can learn how to walk or even turn left and turn right. And you can look at, like the post-transfer performance ends up being substantially better than doing domain randomization or just using a simplified mode. So what is the takeaway over here is, for some problems, we might have analytical models which are available. So we don't need to learn what we have, but we can just learn what is required. So okay, so let's see. So are there any questions over here? I do see, 2 questions in the chat, or a couple of questions. So one is, what if K ends up being just as complex as F4? So what you mean is if the analytical model is super, super simple, right, then in that case, yes, in that case, you won't get a lot of savings. But if the analytical model gets you half the way or 3/4 of the way, then you could get, significant amount of savings. It really depends on the problem setup. The second question I see is, what is the difference between decomposing F full is equal to F simple plus F res? Anubhav, I'm not sure if I understand your question. So maybe if you want to speak up, that would help me answer better.
Yeah.
Go on.
So compared to the method you just described, so it sounded like we were learning how to modify the input into the simple simulator such that the kind of the simple simulator tracks the like real world dynamics. But I guess like one thing that's often done, right, with residual dynamics is you would say like F full is equal to like F simple plus F residual, and then you would learn the function F residual. Does this method like on this slide have a major advantage or disadvantage compared to that?
So you could, do that kind of, things also, but depends on what you're controlling, right? If I'm controlling the, if I can put in the accelerations and input that at the next time step, it is much more, that it's easier to, do the learning. So I think, okay, so I think in general, there is I don't think in general it is true that the method I'm presenting on this slide is going to work better than just having f simple plus f residual. But there are certain cases in which it gives a benefit, right? For example, over here, I'm just dealing with accelerations, right? Now, suppose if I want to switch on gravity, it becomes very easy for me because I can just add gravity to my acceleration vector, right? Versus if I'm learning, f simple plus the residual, then I have to relearn, if I am changing the gravity, for example, or if there's some external forces which are being applied, I cannot easily account for them.
Right.
Right? So
Okay.
because of those considerations, it might be useful to represent in this particular way.
Okay. Cool.
Yeah, but this is not, so this is maybe specific to cases where forces could change, right? But maybe in some other setup, the two models could be equivalent, could provide the same benefits, right? I mean, the one you suggested and the one I'm presenting over here. Yeah.
And I guess like one follow-up question, could you do the same kind of thing but in reverse, right? So instead of learning a way to map your like U full into U simple, learning a way to map U simple into U full so that F full, like the dynamics seen in the real world, kind of match the dynamics that were simulated.
I mean, you could do it, but it's not very useful, right? Because you want to operate in the real world, right? Eventually. So it wouldn't really help you, right? Because you'll end up matching what happened in the simulator. So that you wouldn't be able to transfer the policy.
Right. Okay.
Okay. Then I think the last question was, is a residual just one layer network? No, it could be a multi-layer network, right? I mean, you can just think of the inputs are Q, Q dot, and U full, and we output U simple. So this can be a multi-layer network over here. Okay. Any more questions over here? Nope. Okay, so well, if you have any more questions, maybe we can chat, at the end of the class. So let's, keep going and just recap, what we have learned in with models. So the first question we started off with, or one question was, why are models useful? One thing we saw is increase in my data efficiency. And so I'm just re-showing you the video and the curve that we had, which said models can increase sample efficiency. And why can they increase sample efficiency? Because I can swap the actual world with the model of the world, right? And then I can take those actions not in reality, but in imagination. And that is what leads to the sample efficiency. So I did not cover, DynaQ, which is the most classic model-based RL paper. So we have covered all the concepts, but in a much more modern context with deep networks. But if you're interested, I would suggest reading the DynaQ paper. Anyway, so that is because I can replace the world with a model, leads to sample efficiency. But sometimes using the models can come at the cost of peak performance. Now, why is that? Because the model is trying to learn a dynamics in all parts of the state space, right? So it might not approximate the part of the state space which is essential for the task, right? For example, there could only be a very narrow chunk of the state space that I need to model. And if I model that very well, I can solve the task, but I don't care about other parts of the state space. And this would be an issue if the model is learned in a task agnostic way. And that's why we saw that because of this, we could have this loss in peak performance. We would typically interleave model learning and RL together. Or as we saw in guided policy search, and we could use trajectories from models as initialization for RL, right? And then iteratively do this process. But if we do either one of them, then generalization to new tasks becomes hard, because if model learning and RL are interleaved, it means that I am biasing my model to work well for the kind of data which is necessary for solving that task. Right? So there's a trade-off between learning a general model versus achieving very high performance on one task. Any questions on this part? So Dongchi, you have a question. Says, is it possible to incorporate learned models in the policy gradient theorem? So do you mean using the learned models to generate data, or do you mean something else?
Yeah, I think I was curious whether after we learned the transition reward dynamics, because I think one way to use the model for better sample efficiency was to generate the samples in the environment. But I wonder, now we have a transition reward function. When we estimate the Q, I guess, is it possible to incorporate the models there so that we can have a better policy gradient learning? Some random thoughts, but I was curious.
So if you have a model of your reward function, right, and if you have a dynamics model, right, that means, and suppose if your models are differentiable, that means you don't need to do reinforce anymore, right? Because you can just do a differentiation end to end and get the gradients with respect to the actions, which can help you choose the actions, right? So you get rid of the variance which comes from reinforce. On the flip side, what you don't get is, if the time horizon is very long, then your model predictions can become worse. Therefore, your gradients can become noisy because of that for long-term problems. So if you have a short-term problem, if you have a model, then you don't need to do reinforce, right? I mean, I can directly optimize. Does that make sense? Okay, cool. So there's another question, says, just to confirm, learn models hurt peak performance that you would have got using model-based control. No, so what I'm saying is, if you do model-free control, and if you're willing to throw in a lot of data, for example, right, and you get some performance with respect to that, or when you interleave model learning and RL together, and you get some peak performance, right? So suppose those are two scenarios in which I get some performance. Now, if I'm learning a model without the task, I get my dynamics model, I fix it, and then I just do RL with that model, or if I do trajectory optimization with that model, that performance could be lower. Does that clarify your question? Okay, cool. Perfect. Okay. So now, what are some open questions in this area? So, one question is, to get, as we were discussing, to get high performance, we would like to have our modern learning methods get influenced by the task. So it still is, an open question, how can we balance this trade-off? The other question comes up is with context with to inverse models or goal conditioned RL that we looked at in the last lecture. So one question is how to generalize to out of distribution images. And the second question is how to specify goals. So how to specify goals is something we covered in the last lecture. Let me focus on the first point over here. So what do I mean by out of distribution images? Right. So suppose, an example we saw was, given this current image and this goal image, I want to have my robot move from the current to the goal image. but this goal image actually comes from the same environment, right? So you can see this couch over here. So this goal image is coming from the same environment. But what if, if I were to put a goal image from the internet? Right? So now this still depicts a couch, but is out of distribution in the sense that I haven't seen these kind of images in my environment. Or another thing I could ask is go to a new category of objects that was not encountered in your training set. Or maybe, at some point you want to just say a word couch and want my system to go over there. So how do we, go from, goal conditioned reinforcement learning policies, learn in one environment, and allow the goal specification to become more abstract, right? Going from the image or an observation in the same environment to maybe observation from a different environment to eventually maybe even going to words. So that remains an exciting area of research. And one other thing that you can take away is that these goal conditioned models are a very natural way if you were to give language instructions or instructions in some more abstract form than maybe just a reward function or an image of how you want the world to look like. Then another question which comes up is what exactly is a model? So until now we discussed two kinds of models, the forward model and the inverse model. But turns out there are many different kinds of models. For example, if I'm doing navigation, then what my system cares about is where are obstacles and where there are no obstacles. So we just want an occupancy map of the environment. Versus if I'm trying to push objects, what we care about is Newton's physics, because that controls how the object is going to move. Now a map is a very different kind of a model than physics. And now imagine, if we are playing games, then the models that we have are again different, right? There might be game rules, right? Of, what can, these different, what can the opponent do? What can the opponent not do? Or for example, over here, just knowing that the bullet can hit this enemy and this enemy is going to die, which will give me some more points. So we have, maybe relational models when we are doing gameplay. And many times, these models, the optimal model is task specific. And an open question is, could we figure out what is the appropriate model for the kind of tasks that we are doing? Right? For example, if I'm doing navigation, would my system automatically come up with a map as the right model? Versus when I'm doing, pushing objects, it will end up being physics. So how do we address this question? Another open question is, if we were to build a forward model, what is a good representation for it? Some of it we'll touch upon in this lecture. And lastly, if we do have analytical models available, then how do I combine the best of both worlds of learning and analytical models? Any comments, questions, discussion topics over here? Nope. Okay. So now, I'll take like a brief, a digression. It's not a digression. It's, something to know about, which is successor representations. The successor representations are some things which sit in the middle of model-based and model-free methods. Right? It's not something super popular. It's much more popular in neuroscience than it is in artificial reinforcement learning, but something definitely to know about. So what is this thing, right? So let's look at the value function. And The value function is expressed as the sum of future rewards. Now I'm going to simply rewrite my expectation by realizing the expectation as the probability. Right? So this is just writing down the definition of expectation. Now, what I can do is I can interchange the order of summations. So now I have summation over S prime, then summation over the entire trajectory, and then R of S prime. This is, I'm just changing the order of summations. So now instead of saying the value function is the expected sum of rewards, what we can say is let's first calculate how often is a state S prime visited in the future and multiplied by the reward I get in S prime. And let us sum it up over all possible states. That's an equivalent way of stating the value function. But what this way of stating allows us to do is it allows us to segregate some function M, which calculates how often S prime is going to be visited in the future under my current policy, and the reward function. What is this M again? This M is how often, or the expected number of times I'm going to visit state S prime in the future. And this is known as the successor representation. So it is model-based, kind of model-like, because it is separating state transition from rewards, just like a forward model would separate dynamics from the rewards. But if I have a forward model, to find the action sequence, I need to do all of this optimization of the action sequence. And that can be expensive or costly. But evaluating the successor representation or using it is more like a policy. Right? So there's no search. So this is, evaluating the successor representation is, more like a model-free phenomenon. Right? So, therefore, people think of it, something which is successor representations as, something in the middle of being totally model-like or totally model-free. Right? It just depends on how you squint. So the definition of successor representations clear? Or what is it? Okay. So I see there's a question, which is what if the reward depends on where you approach S prime from? So you're saying if the system is not Markov, then what would happen? So what I've written it down is for a Markov, Markov decision process. If it is not Markov, it will become tricky. Then we can use the kind of tricks we had where you can convert a non-Markov problem into a Markov problem by augmenting the state space and then use the same formalism. Does that answer your question, Dhruv?
Yeah, sort of. But even if it's a Markovian system, wouldn't it depend on what the previous state before S prime was? Like right now we know like the initial state and the final state, but like not any of the states in between.
So typically when you have, like your Markov system, I'm assuming my reward, depends on S prime, right? I mean, you're saying what if the reward depends on, S prime and S, right? Or S minus one, then what would happen?
Yeah, just like S prime and ST minus one. Yeah.
Yeah. I mean, so in that case, I would get an augmented state space, right? So I have like, like two states, like pairs of states. Right. I mean, if I cannot express my reward function like that, then I really can't write it down. I can't write on the successor representation in that scenario. And so just think of it. You're saying there's reward dependent state 1, 2, 2, 3, 3, 4, 4, 5, right? So I can make 1, 2 as one state, 2, 3 as one state, right? 3, 4 as one state. And in that case, the rewards are just depending on the state and not on the previous states, right? And then I can still rewrite this.
Yeah, got it. Thanks.
Okay, so now let's look at how the successor representation behaves. So for example, I have my agent, we have some walls, and here is a goal, and we allow a random policy to explore. And then we can look at the expected count of the states it visits. Right? So for example, this will be the successor representation, right? Where the z-axis is showing how often I visited a state. So what you find is, naturally, the agent will be stuck near the walls. It will not cross the walls very often. The successor representation is going to be low on the other side of the wall. So, as opposed to, L2 distance between the states, successor representation can, accurately describe the state connectivity. But that's something expected because the way I'm calculating the successor representation is to compute what are the states I'm going to visit in the future. Then as we do learning and the policy converges, the successor representation is going to change. And this ends up being my final successor representation, which says, that I'm visiting these states more. And then as I go towards the goal, you see that there's a hump, but the hump reduces over, as you get closer to the goal. That is because of the discount factor, right? Because if you are computing the successor with respect to the initial state, the discounting would downweight the states close to the goal. So therefore, you see this linearly decreasing trend as we keep moving towards the goal. So now one question which comes up is, suppose if we were using the successor representation, and if now I change the goal, suppose the goal is not over here, but the goal is say somewhere here or somewhere here, right? I change the goal position. So what happens then? So I think we have a small poll for this. I want to launch the poll. And the question is, if we change the goal location, would the successor representation help in quickly adapting the policy? And there are three options. So we think about it for 30 seconds. And I encourage everyone to answer. Okay. So seems like we've got some votes and some people are still on the fence. So I encourage everyone who's on the fence to make your vote. We are closing it in 5 seconds. So 5. Okay. So let's close it. So let's see what people think. Most of you that it will depend on the new goal location, right? I mean, now why is that? Right. I mean, the reason why that might be the case is if the goal location is along the path that the agent was following, then it is very easy to deal with a new reward function because my dynamics because my successor representation is not going to change. Just the reward. I just have to focus on which state gets a high reward. But if my goal was, say somewhere over here, my successor representation is going to be a very bad representation because now I have to relearn the successor representation to relearn the reward for a new position, right? So this split between my state transition and the dynamics and the reward function would not really be useful. But in many scenarios, it is useful. And I'm just going to show you a couple of examples where it is. So here's one problem where I have an agent and I could have 3 setups where reward is given in 3 different positions, either over here, or over here. And we have a random policy which is initially exploring the environment, say starting from the top position. And first we train on reward 1. Then after some time steps, we decide to change the reward to location 2, then to location 3. And what we're looking at is a comparison between a model-free system and a one based on successor representation. So what you see is on the first task, both the model-free and the successor representations learn almost as quickly, right? And that's expected. But once we change the goal, the successor representation is able to adapt very quickly. And the model-free system takes much more time to adapt. And in the time window that we are seeing, it does not actually ends up getting as competitive. So, here is, one scenario where if I have a good exploration policy and, my rewards are, maybe within the set of states my exploration policy visits, then successor representations could allow us to change goals very quickly, as opposed to a model-free system. If you're interested more, I recommend reading this paper, Hippocampus as a Predictive Map. When some people also believe in neuroscience that successor representations are one of the things that the brain also uses to solve decision-making tasks. Now, I'm not saying that is the thing the brain uses. It's one of the things which people in neuroscience believe the brain uses, not the only thing. Now, there have also been extensions of successor representations to deep learning or with deep reinforcement learning. So a good paper is Deep Successor Reinforcement Learning by Tejas a couple of years back. And they consider maze navigation, but also Wisdom, which is a first-person shooting game. And I think the main takeaway over here is, so if you look at DQN, and then we look at which is in the dashed line, and then we have successor representations in the solid lines. And what they're showing is that as we change the reward that is there, so I'm starting at the green location, but I have to go to the yellow location. So my reward could be 1, 3, or 5. If I change the reward, right, my successor representation is able to get to that reward much more quickly than DQN, which reaches it the right values, but it takes much more time to reach there. So, what's the takeaway over here? The takeaway is that in some situations, successor representations can help you change the goal quickly. Any questions over here? No? Okay. Then if you want to look at one lab which does reinforcement learning and really works on successor representations, I recommend you check out Sam Gershman lab at Harvard. I think he has some very nice paper on successor representations. So now let's move on to this next problem, which is feature spaces for model learning. Now, as we did in the last lecture, let's take a 5-minute break, and then we will jump into this topic. So we'll start right at 11:55. Right, so it's 11:50. We'll start at 11:55. In the meantime, if you have questions, post them on chat. I'm happy to answer. If not, I'll just close my video and see you in a couple of minutes. Okay, so let's resume. So we left off at this question of feature spaces for model learning. Now, if you recall, we talked about forward models and we talked about having some feature space Z, and we can make a prediction about the future in this feature space Z. And the question is, what does this feature space Z needs to be? And how do we use this feature space Z? It's simply, I have, say, my image is O. We have some encoder which maps it to this representation S plus over here. So S plus is my feature representation of my state, which is the same as Z in the previous slide. So one common way to learn this feature S is to reconstruct my observation O. And so this part which goes from the image to the feature is called the encoder, and the part which goes from the features to the observation is called the decoder. And then using this feature space, I can take an action. Then I get my prediction of the feature space at the next time point, and so on and so forth. So instead of instead of doing dynamics in the observation space, we can do dynamics in the latent space. So we have seen how we can do dynamics and how we can optimize the action sequence given a dynamics model. But I think a more relevant question over here is, why is reconstruction a good metric to learn a state representation? So one intuition, or one of the original intuition, actually came from Horace Barlow, who was a computational neuroscientist, but he did a bunch of other wonderful things also. And one of his findings was that the brain compresses information. That if I get a high dimensional observation, the brain is going to reduce it to as few bits as possible. And this inspired a lot of work, such as autoencoders, Boltzmann machines, sparse coding, independent component analysis, and so on and so forth. So one of the popular implementations of this idea comes in the form of autoencoders. Now, what are autoencoders? We have input data X. We want to map them into some feature Z. We're going to also call them A in the future, from which I can reconstruct my data. And my loss function is X minus X hat. So now if my Z and my X are as big, then I can just learn the identity function. So in that case, I wouldn't really learn any meaningful features. But typically, when people construct autoencoders, they would ensure that the dimensionality of Z is much less than dimensionality of X. That is, I need to compress my data before I expand it again. And this compressed feature space Z is hoped to be a good feature space. So how does this look like? I'll take my input images. I'll take some images as input. I could have a convolutional network and a deconv network, and I can produce image outputs. And whatever I learn in the middle are my features. So this is also called as an autoencoder with a bottleneck. Why is it a bottleneck? Because the dimensionality of the middle layer is much less than the input layer. So you can think of autoencoders as doing non-linear dimensionality reduction. So if I have some data, we all know about PCA, which is a linear method for doing dimensionality reduction. Autoencoders are a non-linear way of doing the same thing, which models the data much better than PCA. Right? So if you want to think of it, you can also think of autoencoders as deep PCA. So to give an intuition of what happens when you run autoencoders on images, suppose I take this image, I take small patches of the image, and then I train an autoencoders on these patches. The learned representation ends up looking something like this. Right? So this is my low dimensional representation of the patch. And what is this representation? It ends up being edge detectors. So now this initially was very, people were very proud of this finding that if you ran, autoencoders on image patches, you would end up getting these edge filters. Because if you look at the human visual cortex, the first layer in the visual cortex also has edge detectors, right? So they thought maybe this is a very general principle of feature learning, which can explain how features are in the human brain. So therefore, it could also lead to significant advances in computer vision / artificial intelligence. Now, instead of having a bottleneck, another way to induce compression is by imposing the sparsity constraint. And so what we can say is, I want my features to be sparse. So how do we do sparsity? By putting an L1 loss function. Now, you could use sparsity with compression too, if you wanted to. Or many times, people use sparsity with over-parameterization. For example, they will make the dimensionality of A to be high, but like really tune up lambda or make the values of lambda be super high so that only a few of these A's get selected. So any questions on autoencoders or sparse autoencoders? Nope. Okay. Now, one issue which could happen with autoencoders is that we can memorize, or autoencoders can memorize the input, right? Because I'm trying to reconstruct the same thing as was the input. So there's a higher chance of the intermediate layer being specific to the examples in my training set, but not really generalizing that well to my test distribution. And that would be a bummer if that were to happen. So to overcome that issue, there was this paper called Denoising Autoencoders around 10 years back, which said, well, let's take the original image, but add some noise to it. And then I'm going to try to reconstruct the original image. So in this case, my autoencoder cannot just memorize the features, but has to reason about something more in the image. And the paper showed that denoising autoencoders led to better features than just doing the normal autoencoders. So that's what kind of led us, or led the field into one direction, which is feature learning by trying to reconstruct the image, and when we are reconstructing, we try to compress in some way or the other, right? Either by putting some regularization or by choosing an architecture which imposes compression. So now suppose, we have learned this, low dimensional state representation through compression. And, we can now, do dynamics in this compressed feature space. Now, sometimes, the issue, even though we have, learned a compressed feature space, there could be a lot of task irrelevant information, right? For example, consider this image. I might care about this agent to move forward, and all of the background is irrelevant. So even if S is a compressed version, it will have some bits which will represent the background and some bits which will represent the object of interest. So what we would like to do is to only focus on the object of interest and ignore the background. So how do I choose among the small set of features which one of them are good ones? So over here, we can make use of the fact that sometimes rewards are available for the task that we are doing. And we can ask, can I use this reward signal to bias the features learned through autoencoders to make them more task relevant? So we can also try to predict the reward from my state representation and suitably modify the loss function. And so now I'm trying to reconstruct, but also predicting my reward function. Any questions? This was, this idea was behind a couple of popular model-based control papers which have appeared in the last few years. So one of them is Dream to Control. So now what was happening in this paper is we have this observation O1, which we convert into a state S by doing auto-encoding, right? O1 to O1 hat, O2 to O2 hat, and so on. Then we have additional loss function, which also predicts the reward function. And we are doing dynamics. We learn the dynamics model in this feature space. Now, once we have this model, we learn a policy by using this model, right, in a way that we have discussed before. And then finally, we act in the environment, right, or we just execute the policy. Now, how well does this perform? So here are some results on a bunch of tasks on Mujoko. So one comparison is with A3C, which is the dash red line. And there's another algorithm called D4PG, which would be the model-based algorithms. And model-free algorithms. And then they have, Dreamer compared with some, previous model-based algorithms. So what you can see is, Dreamer ends up improving performance on a bunch of tasks by a significant amount. Right?
I have a question about this slide.
Mm-hmm.
Is when it says environment steps for Dreamer, for example, is that like real environment steps, or is that like simulated the environment steps using the autoencoder features?
The real environment steps.
Okay. So, but in the background
so
somewhere, it's training using the like simulated or the dreamt simulator, right?
Yes.
Okay,
yes.
gotcha.
Yeah. So whenever you see, so no one ever reports the steps which are taken through the model that you have learned, because you don't need to interact in the environment.
Right.
Yeah. So Ayush, you have a very specific question. Let's take it offline about the no value. Okay. Now, if we look at some of the predictions that this model makes, so here is what the ground truth trajectory is. So we feed in first few frames, and then we want to see how it rolls out in the future, and this is the model's prediction, right? So what you see is it kind of starts off being similar. At some point, it ends up diverging, right? Same over here. It starts off being similar, but then in the end, it starts getting blurry and starts diverging. So this is what happens. This is the problem we were discussing before, right? If we try to roll out for long with models, my predictions can become inaccurate. Another, so in this line of work, or not in this broad space of ideas, another paper which is interesting is the value prediction network. It has, it's quite similar to Dreamer. So we again have this image X as input, which we encode into a state. And now we are predicting the reward function. We are, predicting the next time, but we are also predicting the value function, V of S prime. I think Dreamer also predicts the value function. So, these two papers, came out about the same time. So there's a lot in common, and what is different is really in the details. So if you really want to find what is different, you should read the papers. But I'm going to give you an overview of, how these or what these methods are, so you have the right pointers to look into. And the input over here, instead of it being just one action, it is a sequence of actions. Right? It could just be one action also. Now this is, what is happening at one step, but we can roll it out at multiple steps. And, this is exactly what we were seeing with respect to Dreamer. So now how is this system learned? Right, so at every state, X1, we predict, X, K steps in the future, what is going to happen. We take an action, we come to the next state, we also predict what is going to happen in the future, right? And this is how you would roll out the agent at training time. Now, what is the loss function? It's I encode my X into representation S, and I learn the transition dynamics. Now, I'm going to predict the value of the state, right? So now the key difference over here is that they will not be reconstructing the input, right? All they're trying to do is they're trying to predict the value function and only use the value function to learn the state representation, right? As compared to Dreamer, which is also trying to predict the state. And why were they doing this? They were doing this because their argument was we only should capture features which are predictive of the value. All the other features are going to be irrelevant. So we really don't want to capture them. Right? And then we have our reward prediction term. So I'm learning my state representation by trying to predict the value, the reward, and what state is going to happen in the future. And this ends up being my objective function, where the summation is over K time steps, which is K time steps in the future, I'm making the prediction, right? So I take the loss with respect to prediction at 1 time step, 2 time steps, 3 time steps, so on and so forth. So this is the model learning process. And now, once I have this model, we can use this for planning, right? So I can now simulate many different trajectories through this model, and then find the one which leads me with the maximum reward. Right? So you can just do something like a tree search, if your action space is discrete, for example. Right? So they show, some results on, these toy domains where this green guy has to capture as many blue blocks as possible. And what they show is that depending on how long the planning horizon is, the agent comes up with different strategies. So for example, with A, if I tell you have 20 time steps, you come with a different strategy. If I tell you only have 12 steps, you come with a different strategy. And this behavior is fundamentally different from a model-free system, right? With a model-free system, it's very hard for you to tell, that you should go with 20 steps or 12 steps. Right, you will have to retrain with maybe like a different reward function. One thing you could imagine is you could specify the number of steps as part of your state representation. That would become a goal conditioned policy. That could, display such behavior, in theory. But as compared to not a goal conditioned model free system, this behavior ends up being quite different and characteristic of a model-based system, that I can put constraints at my test time or evaluation time, which I can satisfy because I do have access to a model instead of just having access to a policy. Then they also end up showing improvements in results on a bunch of Atari games. So this is, an overview of value prediction. What did we saw? So just to recap, so what we saw is first, we said we can learn good features by compression. Then we said, well, if I'm compressing, I've reduced my image into a low dimensional state, but there can still be some irrelevant stuff. So what Dreamer does, or Dream to Control model was also called as Dreamer. So what Dreamer does is to say, to choose these features, let me also predict the reward and the value function, right? And that can help me choose good features. What value prediction network comes and says is, well, don't really predict the state, don't reconstruct the state, just predicting the value should be sufficient. And they showcase their results on a bunch of standard benchmarks. So a question on the chat is, what is the y-axis over here? This is the game score on these plots. So, okay, all well and good. But, turns out that there are issues with autoencoders also. Right? I mean, what is that issue? So I have this image, which I have a bottleneck of 10, 10-dimensional bottleneck, and I'm reconstructing the image back. Now, what I'm hoping is that by compressing, I'm able to learn these independent factors, right? Or some good features about images. For example, if I have natural images, well, you could expect that, oh, maybe I will learn about to separate out shape from color from lighting. Right? Because if you look at the physics of how image forms, you have some shape, some light comes in, depending on the texture or the color of the material, the reflected light looks of a certain kind, right? Of a certain color. So you could expect I'm going to learn, features like this, which would be a good compression of my data. But it turns out that there are other ways to compress it also. For example, JPEG compression is also a very good way to compress it. Right? How does JPEG compression look like? These are the features which JPEG compression would capture. Right? I mean, some very high frequency features, some very low frequency features, but these features are not semantic at all. Right? So, one issue with autoencoders is that they could end up compressing, but it's very hopeful that the compressed features are going to be semantically meaningful, or they're going to be the features that we really care about. In some cases, they could be. In some cases, they're not going to be. And that is why what this previous works did, by putting in this reward function or the value function term, was important. Right? Any questions over here or any comments from anyone? No? Okay. Now, let's look at the example that Dreamer was working on. So Dreamer was working on this agent moving forward, and we can compute the return of this agent across a bunch of different model sizes, small, medium, and large models. But let's make this background be somewhat complicated. Right? Let's have these distractors also. What you now see is that the performance, first of all, is much worse. Now, why is that? Because if I'm reconstructing, I'll also end up paying attention to the background, and I'll need to spend energy modeling the background. Right? This is, again, verified by the fact that as my model size is increasing, my performance also increases, right? Which is suggesting that most of the model capacity is being used in modeling the background, right? Instead of really modeling the right thing. Right? And where we left off the previous discussion was to say that we can use the rewards to learn task or choose the task relevant features. But the reward prediction doesn't really solve everything. Right? The reason is that predicting the reward can require very little information. For example, suppose I have this agent, right? And I want it to walk on the right. Then just representing the velocity of the center of the mass is enough to predict the reward. Right? So I just need to capture the velocity of center of mass. I don't really need to capture any of the joints. But if I need to act, I need more information, right? I need to know the pose of this agent or the pose of this humanoid to say what commands the humanoid needs to execute next. So on one hand, reconstruction is maybe capturing too much information. On the other hand, rewards are capturing too little information. Right? So therefore, we need to tune this term lambda which is trading off too much versus too little, right? And this choice of these hyperparameters becomes quite tricky. And you really have to tune this to get, good performance. Now there are, more recent works which are looking at, how we could simplify this tuning or, make some changes in the setup so that, this trade-off is simpler to make. Right? And some of this work, will appear at ICML. So if you, are into research, maybe you would want to check out, a couple of these papers. Any questions on this part? Nope. Okay. If not, then what we're going to now look at is, well, so we looked at one way of doing feature learning, which is autoencoders. What are some, possibly other ways of doing feature learning? So I'm going to reuse, is my slides being shared? So I'm going to reuse. Are you seeing my screen? No. Are you seeing my screen or you're not seeing my screen?
We
I
are
have no
seeing.
idea. You can see the slides, right? Okay. Cool. Okay. So I'm just reusing the some slides, from like 6S090, which is the course which our lab offers in IAP, right? I think this has a good summary of some feature learning techniques. Right? So autoencoders was one thing which was unsupervised. The best way to learn, or one of the very popular ways to learn features using supervised learning, right? So any task I have, I can, get some labels, but, as we know, annotations are time consuming, right? For example, if you have to segment this out, this is going to be time consuming and it's going to cost us money, right? So annotations are expensive, right? So for example, if you need to get, 14 million images annotated with segmentation mask, you might end up spending, around $7 million, right? A lot of money to be spent. Now, because of this, there was this other trend which came about, which was weakly supervised learning. When the data is easily obtainable, but was not explicitly annotated by humans, right? What do I mean? For example, on Instagram, there might be, some comments or, these hashtags which are there, right? So these hashtags are providing like a weak kind of supervision for what might be there, in the image, right? For example, so you can use Instagram tags as labels, right? So this is data which is available, but is much more noisy than getting, high quality annotations. The other thing you can also imagine is that, for some images you get high quality annotations, and for many images you don't have annotations. Then how do you, use some unlabeled images and some labeled images together? Right? So that is called as semi-supervised learning. Right? So there's supervised learning, weakly supervised because the labels are not perfect, and then there's semi-supervised learning. Right? And then the most extreme form is unsupervised learning, where there is no human annotation involved at all when we are generating data. Right? Now, what is good examples of it? So autoencoders are one good example, right? Because I can just take the image, cut it. Right? In that case, I don't need an annotation from the human. Another example is, colorization. For example, I can make the image grayscale and try to predict the color. Now, why should this be a good task? Right? I mean, the reason is, in order, so there are some things which are true of the world. Like, for example, we know that grass is green, and we know, that dogs have a certain color on them, and we know how the eyes look like, and the nose is typically going to be black, right? So in order to color the image, there's a lot of semantic information I need to figure out. So therefore, the features that we might end up learning by performing this colorization task could be semantically meaningful. Similarly, we could rotate the image and try to predict what the rotation is. This would again mean that I have to, figure out, like what is the correspondence, say, between the eyes over here to the nose in this particular image. So these tasks, although look very simple, but they are forcing some reasoning which might involve semantics or other useful computations or other useful feature computations. Right? And the labels over here are automatically obtainable. Right? I don't need a human. I just need to define one function, and then that function provides me the labels. In autoencoders, it is reconstruct. In colorization, it is a color. In rotation, it is the amount I rotate the image by. And we can use these techniques on large amounts of unlabeled data, coming from various different sources. So a popular question became, in representation learning, became, how do I find a good task? Right. So I talked about a couple of different tasks over here, right? Colorization one, rotation one, autoencoders one, action prediction, like the inverse model is another. So there was this whole cottage industry of different papers proposing different tasks, right? And each task, and then the whole game was, what is the task which works the best? So we looked at this autoencoding business. So I'm going to skip the autoencoding business. And what works the best to date is something called as contrastive learning. And what does contrastive learning do? It takes, for example, one image and it would transform the image. For example, I can crop the image, I could rotate the image, I can add noise to the image. So it's some form of data augmentation. Then we say that this image and the augmented image belong to the same class, and all other images belong to a different class. Right? Or another way to say it is, I want to push the features of the original image and its augmentation close to each other, and I want to push the features of other images away from it. Right? So note, these other images could contain an elephant, but they could also contain cats or dogs. Right? So these negatives are not based on semantics. They're just based on the image identity. Right? I take an image, its transformations are positives. All other images are my negatives. Right? So this line of work has been going on for a long time. It culminated in papers like Sim2Clear, which got really good performance. For example, if you compare ResNet 50, right, and if you're looking at ImageNet, the gap between using 1 million labeled images versus not using any labels was only 2%. Right? So we were able to come up, or the field was able to come up with good methods of learning features without requiring human annotation. And in the envelope of supervised learning, got also pushed quite a lot. I think early this year, there were 2 papers which came out. One was DALI and one was CLIP. So what was these papers doing? So especially the CLIP paper was focused on representation learning. What they did was they took images and they took captions corresponding to images, right? For example, Pepper the Aussie pup, right? Or some description of the image. Then they encoded the image and the text, and the text encoding was through transformers, and they tried to match which image goes with what text, right? And there was a loss function which said if image and text correspond to each other, reduce the distance. If the image and the text do not belong to the same corresponding pair, increase the distance between them. Right? And this ended up getting, so this is the blue line is the performance on ImageNet with 21,000 categories. Now this, the CLIP model ended up doing, much better than like the existing ImageNet models. And some people, call it weakly supervised, because the way they generated data was they took captions from Wikipedia, they put them into Google image search, got images, and got the data that way, right? So now, it's up to you, of how you think about it, right? I mean, in some ways you could say, well, Google did all the work, right? Because they collected all the data already for them. So, but you could get this data, available where, there are descriptions of images on Instagram, Facebook, so on and so forth, right? So, up to you on, how you want to think about it. But, this is the latest and greatest we have in representation learning right now, right? So with that, I'm going to stop and take, maybe one quick question.